You know, the world around us can feel pretty random sometimes, right? But what if I told you there's a hidden order to a lot of it? Today, we're going to unlock that structure using continuous probability distributions. Think of them as a powerful mathematical language that helps us model everything from complex engineering systems to the simple patterns of the natural world.
So let's just jump right in with a question. Think about it. Waiting for the next customer to walk into a coffee shop, measuring the birth weight of a newborn baby, or even trying to predict when a light bulb will finally burn out. I mean, these seem like totally separate, unrelated things, don't they? But believe it or not, they share a really deep connection.
And that connection is that we can describe and even predict all of them using the language of continuous probability distributions. These are the mathematical models that let us find the pattern hiding in the noise. They help us understand things that don't happen in neat, countable steps, but happen across an infinite, continuous range. So here's our game plan for this explainer. We're basically going to build a statistical toolkit together. First, we'll talk about the big shift from counting things to measuring them. Then we'll add 3 essential tools to our kit: the uniform, the exponential, and of course the famous normal distribution. And finally, we'll figure out how to pick the right tool for the right job.
Okay, first things first. We really need to get why these models are even necessary. And it all comes down to this fundamental leap you have to make in statistics, the jump from counting things with whole numbers to measuring things that can have any value at all.
So, what this all boils down to is the difference between discrete and continuous variables. Discrete variables are things you can count, like the number of heads you get when you flip a coin 5 times. The outcomes are separate and distinct. But continuous variables are things you have to measure, like height, weight, or time. They can take on literally any value within a range.
And because of that difference, we have to completely change up our math. For discrete data, we use what's called a probability mass function, or a PMF. But for continuous data, well, what's the probability of someone's height being exactly 175.000 centimeters? It's basically 0, right? There are infinite possibilities. So instead of adding up individual probabilities, we have to use calculus to find the probability over a range of values, using something called a probability density function, or PDF.
All right, now that we've got that distinction down, let's start building our toolkit. And our very first tool is the most basic, most fundamental model of randomness you can get. It's the baseline for when you have no reason to believe one outcome is more likely than another: the uniform distribution.
People often call the uniform distribution the rectangular distribution, and honestly, that shape tells you everything you need to know. That perfectly flat top means that within a certain range, every single outcome has the exact same chance of happening. No favorites here.
So the official definition is that a random variable has a uniform distribution if its PDF is just a constant value between a minimum point A and a maximum point B. And that constant height isn't just random, it's calculated very specifically as 1 divided by B minus A. And that just makes sure the total area of our rectangle, the total probability, is exactly 1, which it always has to be.
So, when do you actually use this? Well, it's the absolute cornerstone for generating random numbers in computer simulations. And in engineering, it's used to model things like system noise or quantitation error, where you just assume the error is equally likely to be anywhere within a specific range. It's really the purest model for unbiased randomness.
Okay, time to grab our second tool. While the uniform distribution is all about where a random value might fall, the exponential distribution is all about when. This is our go-to model for figuring out the time between events.
The exponential distribution is perfect for modeling the time that passes between independent events that are happening at a constant average rate. We represent that rate with the Greek letter lambda. Just think of lambda as the average number of events, like customers arriving or text messages coming in, per hour or per minute, or whatever unit of time you're using. And this thing pops up everywhere. In reliability engineering, it models how long until a machine part breaks down. In business, it's used in queuing theory to describe the time between customers arriving in a line. It's even used in finance to model the time until a loan defaults, and in telecom to model how long phone calls last. It's incredibly versatile. But here's where it gets really weird and fascinating. The most unique property of the exponential distribution is this: it's memoryless. What's happened in the past has absolutely zero bearing on what's going to happen in the future.
So what on earth does that actually mean?
Okay, let's use the classic bus example. If the time between bus arrivals is exponential, and you've already been waiting at the stop for 10 minutes, the chance that the bus will arrive in the next minute is exactly the same as it was the moment you first sat down.
It's like the clock completely resets every single second. It's bizarre.
And the craziest part is that this means the expected time you still have to wait is always 1 divided by lambda, that rate parameter. It doesn't matter if you've been waiting for 5 seconds or 5 hours. This has huge implications for things like product warranties. If a component's failure rate is exponential, a part that hasn't failed yet is, from a probability standpoint, as good as new.
All right, on to our third and final tool. And let me tell you, it's a big one. This is the absolute celebrity of the statistics world, the one you've definitely seen before, the normal distribution, also known as the Gaussian distribution, or, most famously, the bell curve.
And it is absolutely no exaggeration to call this the most important distribution in all of statistics. Why? Well, it's because of a powerful concept called the central limit theorem. The short version is that when you add up a whole bunch of small, independent, random factors, their combined effect just naturally settles into this beautiful, predictable bell-shaped curve.
So what makes it tick? Well, the normal distribution has some really elegant properties. It's perfectly symmetrical. Its mean, median, and mode are all the exact same number, right there at the peak in the center. And you can describe the entire curve with just 2 parameters, the mean, mu, which tells you where the center of the curve is located, and the standard deviation, sigma, which tells you how spread out or skinny the curve is.
And thanks to that central limit theorem, we see this pattern emerge all over the place. I mean, it's in the natural world and social sciences, things like human height, birth weights, scores on standardized tests, and even really abstract concepts like reading ability or job satisfaction. They all tend to follow this same bell curve pattern.
Okay, so now we have our 3 amazing tools, the uniform, the exponential, and the normal. The final crucial step is knowing which one to pull out of the toolkit when you're faced with a real-world problem.
And looking at them side by side like this makes it pretty clear. If your data is symmetric and every outcome seems equally likely over a fixed range, you're looking at a uniform distribution. If you're measuring the time between events and the data is heavily skewed, meaning you have lots of short wait times and only a few really long ones, you're going to use the exponential. And if your data is symmetric and most of the values are clustered right around the average, well, that's a job for the normal distribution.
Once you master these 3 frameworks, you can really start to see the hidden order in the world all around you. Seriously, from the timing of emails hitting your inbox to the distribution of grades in a class, these patterns are absolutely everywhere. So the real question is, now that you have this new toolkit, what will you explain next?